Hey everybody, welcome to this tutorial on descriptive statistics and pulling them out of data in both Excel and JUMP. What we have is a pretty interesting data set here. I think what I'm going to do for this demonstration is make it a little bit more condensed. So let's copy this sheet so we don't lose this original, right? And now we have this copy, and I'm going to rename it Descriptive Stats so that we can play with this. Okay, now we've got it down to just some columns that leaves us space to actually do our work here. So when we're describing data, we usually need to include several different pieces of information. We definitely need some measure of central tendency, the median or the mode. And then when we're talking about variability, we could discuss the range of a data set. We could talk about the standard deviation, if I could spell, and we could talk about the variance. Right? But then there were two other ways that we could describe a distribution, and that was the skew and the kurtosis. Excel has a lot of functions built right into it, so if you set which cell you'd like your answer to appear in and just hit the equal sign, you can begin writing a function. And what's nice is that when you start typing, JUMP will show you all the different functions that start with that letter. So Excel doesn't call it the mean, they call it the average. Okay, so there are several different options for taking the average, but we're going to stick with just the straight option. So we want to use this average function. You can type it in, or you can double click on it. What's nice is when you double click, it already tells you exactly what it's looking for, right? So it gives you your parentheses, and it says, oh, we'll just start entering what numbers you'd like the average of. We want the average of a whole range of numbers, so there's no way we're going to highlight every single cell one at a time or type them in. So instead, we're just going to highlight them. So I'm going to hold down my shift key, and let's see, let's get the mean. Well, let's take care of this response variable. We'll see what our descriptive statistics are for our response variable. So I'm going to hold the shift key, and I'm just going to highlight this entire column of data, and notice there are 719 observations. Okay, so now I can lift off of my shift key and close that parentheses bracket. So notice you can see what I'm typing in my cell up here in the cell address bar. Okay, so now if I hit enter, it always shifts me down one, but there we go. Here is the mean FSI value. And notice it's giving this to me in scientific notation. If that really bothers you, you can always change the format. You can come into your numeric format and specify that you would just like it to be with decimal places. So maybe we need this to have a couple more decimal places since it was giving us a value. Yeah, we need even more than that. It was giving us a value to the -7. The median function in Excel is just that, median. And since I already have plugged in this range of cells enough times, I've remembered the addresses, so I can just type in the address if I want. So I know that I have column M, and it starts with row 2, and I need a colon here to tell it that I want it to be inclusive of everything in between M2 and M720. And so here is my median value, a little bit different, a little bit lower than my mean, but we don't know if that's significant skew yet. Now the mode, if we were to do this with the mode, we can use the mode function. Again, we're keeping with the simple versions of these functions. And again, it wants us to highlight those cells. So I could say from M2 to M720. But keep in mind here, we have a problem, which is that the data we're working with right now is continuous. And mode is not really a metric that you would use for continuous data, because there's just too many possible combinations of values when you're going out to 4 decimal places, and chances are you won't have any that repeat, or at least none that are meaningfully repeating. This is a good function though to use for more ordinal or integer data, and we do have a variable like that. We have the product index. So let's try mode with a value that it actually should be PIE, product index. Okay, so now if I do the mode function, mode, and I'm going to work with column H, so it's column H2 to H720, close that off, and I can see that the number 7 is coming up quite a bit. But what I can't tell with this Excel function is whether or not it's coming up more than another value that might be higher than this, because remember, Excel will only return the first mode that it encounters. It doesn't tell you if you have bimodal distribution. So using this mode function in Excel really is not ideal. Instead, what I would suggest we do is we use the pivot table and see if we get the same result. So to make a pivot table, I can just stick my mouse anywhere in the table that I want. I come up to Insert, and I ask to insert a pivot table. It automatically highlights what it thinks is the complete data set. And again, it's good that it's not including these. I didn't want it to, because I have this extra blank column in there. So yes, it's selected the correct data range. If it didn't, you could go in and delete this and then highlight all of your data. And I do want it to come into a new worksheet. I don't want to pull a pivot table into the same tab. I click OK, and now I see I have this new data sheet that it's created. I have all of my variables listed over here. I can specify what I want in the columns, what I want the rows to be grouped by, and what I want the values to be reported as. Okay, so in this sense, we were using the product index. So I'd like to see every product index that occurs. So it looks like we have 5, 6, 7, 8. There is no 9 that ever occurs, 10, 11, and 12. So this just shows me all of the possible values of product index that I have. And what I want for the value is just the count of how many times each of these unique product indices occur. And so because I'm not trying to get an average or a sum or anything like that, it really doesn't matter which other variable I use. I just want to know how many times a row is associated with the given product index. So I could use any one of these variables and just get a count on that. In fact, I could even use the product index again, pull that down into my values. I actually want a count, not a sum. So I can click on this little arrow, come to the value field settings, and ask for the count instead of the sum. Notice here, this is where you can also specify other return values you might want, standard deviations or averages, minimums or maximums. So I want the count. I click OK, and now I can see the number of times that each of these product indices occur. And it looks like indeed 7 is our mode, and it occurs quite more frequently than any of our other values. Just to give you an idea of how powerful these pivot tables are, I could try to do this type of analysis, but break it down by, for example, different region. So these plots were split up into northern Vermont, mid Vermont, and southern Vermont. I could take this region and pull that into the columns, and now it actually shows me the count for my different product indices for each of these different regions separately. So it appears that for the middle of Vermont, we don't have any mode, that for northern Vermont, the mode is still 7, and that for southern Vermont, the mode is still 7. All right, so back to our descriptive stats. We're happy now with all of our central tendency values. Let's work on some of our variability metrics. So range, very simply, was the maximum value minus the minimum value. I've already got these sorted, so I imagine I could just look, but you could just as easily, without sorting, pull up the min and max functions within Excel. So we're back looking at FSI. That was column M2. Use my colon and take it all the way to M720. Close out my brackets, hit enter. So there was the minimum value. And I always like to make sure that I'm labeling everything that I do in Excel so that all these numbers make sense to me. Do the same thing to come up with the max. And then I could just take the difference, right? So my range would be equals this minus that. So I have a range of 4.82. Standard deviation has a function that is abbreviated, okay, 0.65. And then the variance, remember the variance is just the standard deviation squared. So I could either do the variance function, which is just var, or I could literally just take my standard deviation and square it. So that's the caret symbol, and then I square it. It gives me this number sign because it's got too many decimals to fit into the cell. Make it a little larger, or conversely, just reduce the number of decimal places, and you can see that we're getting the exact same value. Now, skew and kurtosis also have functions associated with them. Skew is just simply the skew, and so I come out with a value of 1.383. Now, we don't know that this is significant. This is not a test of significant skew, it's just returning the skew. So when you see a positive value like this, right, it means that you have positive skew. And that does make sense because our mean, which is the one that's sensitive to skew, to those extreme values, is a higher value than the median or the mode. That tells us the mean was being pulled to higher values. Let's figure out whether or not this is significant. Let me grab the formula for the standard error of skew. Okay, so we need to get the square root. So the square root function is a fun one, squirt. I want the squirt. And again, I'm going to parentheses just to make sure I get everything right. And maybe it's overly cautious, but it makes me happy. 6 divided by the sample size, which we already had as our count up here, right? And then I wanted to multiply that by 2, right? Because we want to be more than twice the standard error of skew to have significant skew. Okay, so let's multiply that by 2. And this is, oh, this isn't kurtosis, sorry, let's move this, it's confusing. Let's just grab that and move it up here. This is what we have to beat in order to have significant skew. And whether we use the Excel function here, or if we use the standard formula, either way, we're more extreme than this 2 times the standard error of skew. So we do have significant positive skew for this data set, which means we have a lot of extreme high values that are driving our normal curve to the right, to the more positive values. Okay, let's see if we also have kurtosis. The function for kurtosis, is just kurt, and we see that we have a kurtosis value of 3.0. So we mentioned before that if we have positive kurtosis calculations, then we likely have a leptokurtic distribution, the really tall, sort of skinny one. And if we have a negative number, then we have a platykurtic or a flat distribution. Right, so it looks like we do have a leptokurtic distribution. Is this significant? Good question. Let's check out the formula. I'm just going to show you one more little trick that you can do in Excel. So really, the formula for standard error of kurtosis is almost the same as standard error of skew, except it's the number 24 instead of the number 6 in the numerator. So let's just copy it. I'm going to Control C, and I'm going to copy it down here. And I want you to notice that obviously the value changes, and it's because, here I'm going to hit escape so it knows I'm done copying. If you look at the cell values, the addresses that are being used, it's using Y3 for that count, right, to get the count of all the number of observations. But when you look at when we copied it, it's now using Y5, and that's because when you copy and paste any formulas or functions in Excel, it moves the address of the inputs to your equation in the same relative way that you moved it when you pasted it. If I wanted to hold that address constant, which I do, I can highlight it and I can hit F4, which really just puts dollar signs in front of both the column address and the row address. And what those dollar signs do is it locks down that cell. So no matter where I copy this formula now, it's still going to use that exact same cell. So I will hit enter to save that. And now when I do my Control C to copy it and my Control V to paste it, I get the exact same value because it's still using that lockdown Y3. All I had to change then was the 24 to get the standard error of kurtosis. And it looks like I also have significant kurtosis because I am more, and what I've calculated for kurtosis, I am more than 2 times the standard error of kurtosis. This is a distribution that has both significant skew, positive skew in this example, and also significant kurtosis. And that would be a leptokurtic distribution, very peaked. In all, when we consider all of these different descriptive metrics, it appears that we do not have normally distributed data. So that's going to inform the types of analyses that we can do throughout the rest of this research study. maybe you'd like to identify outliers and you want to know what the threshold would be for those outliers. Or maybe you want to figure out the percentile of a very specific year because it had some meaning or there was something anomalous in that year. So that's when we would get into our percentiles. So let's just practice that. Maybe I want to know the 95th percentile, the value of the 95th percentile. So I could use that as a threshold to identify outliers or super anomalous data values as we move forward. So now, again, I'm going to use the percentile function this time. I have to highlight the array. So again, that was M2 to M720. And it's saying, well, what is the percentile that you're looking for? And I wanted the 95th percentile, so 0.95, close bracket that, and I see that the value that is the 95th percentile for this data set is 1.256. And what this tells me is that only 5% of all of the observations out of these 700 and whatever observations, only 5% of them are going to be greater than that 1.256. Okay, and so I can use that as a threshold to identify high outliers. Well, I think we've made this long enough, so I'm going to stop here and set up a different video where we go over the same things in JUMP. And I think by the length of the videos, you'll see how much faster all of this can be in JUMP.